Okay, so in our
So you can analyze that.
okay, we will have a filter design. I will cover the filter design later. Filter design, not on the scope for today's class. Okay, so two things I really wanted to cover. One is what happens if we have an anisotropy in the layers, and there is a homework problem on that.
Kx not equal to ky.
Yes. How do you do that? How you do the problem? I was expecting some questions on that because I haven't covered it yet. Are you able to do it?
Which one?
Just choose the flow lines different from in two layers.
How?
Where the permeability is greater, the flow lines were inside.
So let's get that set.
Yeah, true. I think problem number 4.
Yes. How will you do that? Are you able to do it? So how you do it?
Let's try to like draw the that flow line, and I get the exit gradient from the other side of the.
No.
I'm not sure if that.
Okay, I'll discuss that. If you wanna redo that the problem and upload it again, you can do that. I think the homework is open and will remain open like by end of this week. Okay, so basically, what happens if we have different flow lines, right? Or sorry, what happens if we have a anisotropy and two different permeability? So there are two problems. One is your permeability is changing, and the other one is if you have anisotropy. Okay, two problems. One is anisotropy, the other one is the change in the permeability. So let's say you have first try to discuss if you have only the anisotropy. So let's say you have two different K, and you have a K1 and you have K2. Two layers like this. So let's say you have two different K. If this is a K and the second K, two different Ks. And in between these two Ks, we need to find out like how the flow rate will be. To do that, basically what we have to do is we need to do it as we do it for irregular soil layers. Like there is no anisotropy. So we consider there is no anisotropy and try to draw our flow rate. And then we need to do some adjustment. And those adjustment comes in a way that we cover the changes in the permeability. So what is the permeability? Is it the conductivity or is the resistance? It's the conductivity, right? It's just the inverse of the resistance. So basically what happens when water tries to flow through the lower permeability, what it will have. So let's say you have two different pipes, the same analogy that we try to use before we have the flow rate calculation. So let's say we have two different layers and we're trying to flow the water. So we have two pipes in it. And in between the pipes, we have the soil. Okay. So here is the soil, and within the soil, we are trying to push some water, right? So when the water is going here, let's say here we have a K1 and K2. So in the K1, if the conductivity is higher in K1, means the permeability value is lower, means high conductivity. Then what's going to happen? Here, K1 is greater than K2. Then let's say we have the same flow. Q is same.
in K2, the CPS line will be, the water have to cross,
Water will travel slower.
travel slow, and maybe it has to, the travel path will be longer the than K2,
Why the travel path will be longer?
because there will be resistance. Resistance will be more.
Okay, if the distance is more, then does the travel path is longer?
Time.
Because if the resistance is low,
If the distance is low,
then the water will find its, it will find its way easily through the soils.
permeability is low, means water can pass through it, so
Yes.
resistance is low.
Low. If the resistance is high, water will not pass through it easily.
So it will take longer time, so water will pass through slowly and fast, right?
Yes.
Will take longer time
It will take longer time,
if the resistance, like high.
high and low, okay? So, let me try to give you a different perspective, I really like it, you know? Try to connect civil engineering with philosophy or any other examples. Do you have any idea like how we can connect this problem with any other things that we have learned before?
High flow.
No, not, no pipe, no water, nothing. It has to be completely different. Something. Any idea?
Like if we want to move through a crowd, the crowd is like giving me lots of distance. I try to go around it and my travel path is longer.
Okay, very good example. Like it.
We can compare it with the light.
Okay, very good.
When
How?
light goes to different uh, uh, media, it
Okay,
changes its strengths.
excellent. Very good. This is exactly how light goes through different materials, different medium. Excellent. So, what happens in the light refraction?
From denser medium to a lighter medium, when light tries to pass
Yes,
through the interface,
through the interface.
then obviously the light will not follow the same path. It will kindly tilted towards the perpendicular line.
To a perpendicular line. Okay, very good. I really love it. So let's draw a line here. If light is coming from the lighter medium to the denser medium, which one is lighter? Which one is denser?
The
There one.
the lower one is the lighter.
The lower one is lighter, the top one is denser. So from the dense medium to the lighter medium, what happens?
It will diverge more.
It will diverge more, so it will go away from the perpendicular line, right? So the line is coming in, it's moving away,
Away.
right?
Yes.
Is it moving away?
Yes.
It is.
Refraction.
It's basically same as refraction. Two layers, light is coming, and it will just follow the refraction. The rule of refraction. Got it? Any question? So I'll give you some time to observe it. Watch it, observe it, and ask me the question. Same for you. What is the principle of refraction?
Two principles.
Okay, what is the second principle? I think you already mentioned the first principle.
Sin I divided by sin r equal to the constant, Snell's law.
Okay, what is that?
The angle of incident light with the perpendicular line. The sine of that angle divided by the sine of the reflected light and the vertical line. Vertical line. The ratio is a constant.
Okay,
Snell's law.
okay. Does it apply here? The ratio has to be constant, right?
Yes.
Okay, now let's look into this. You have L1 and B1. There are two things, you know. So at the first one, let's say we are trying to consider that in the flow net. In the flow net, what happens? You have two lines, right? You have a rectangle. In that you have a rectangle in that, or you have a square, not rectangle. You have a square. Within the square, you have two lines, or you have like two sides. One is
Equipotential line.
and this line, right?
Previous line.
So what is the first one? This way. This is flow line,
Flow line.
and in between these two lines are
Equipotential line.
equipotential lines. So in our regular flow net calculations, what happens?
The distance should be the same.
Should be the same, right? But whenever we have two different layers of solid, then we need to be adjusted, right? It cannot be fixed anymore. If the first one is square, the next layer, it should be rectangle because there is a difference. We need to make sure that that ratio is constant. To add, and that ratio adjusted with the changes in the K. Okay?
That is only the regular square.
Say it again.
It will be the regular square.
It don't be the regular square, no way. You have to adjust it in a way so that you allow, you do the adjustment of the equipotential gap. Let me explain it here. So right here, what happens? Look at this. You have a square, right? You have a square. All right. Here, rectangle.
Rectangle.
So how do we do it? Why there is a rectangle? Because within the same flow line, right here, the resistance is lower, right? So since the resistance is lower within the same path, you will have more, you have less drop, not more drop, less drop, less equipotential drop within the same length. So you are adjusting the equipotential drop. So your flow in the first layer, your flow and your drop are equivalent, right? In the second layer, you have the same flow. So if you are accounting the same flow, then within the same flow, your drop is lower, right? So if your drop is lower for the same flow, so you are lowering down the equipotential line.
Dr. Khan, a question.
Sure.
So we're saying that layer two has less resistance. Layer two.
Yeah, that is
It's conductivity.
Layers 2 have more resistance.
Should be more resistance.
Less permeable.
2.5 and
oh yeah.
That was
Yeah.
right.
2.75. Yes. in this travel path, okay. In this travel path, okay, let's try to make it simple.
No comment.
Let's try to do a problem. And in this one, let's say we have another layer, two layer. Looks like this. Okay. Let's consider like this. So two layers. Now in the first layer, let's say, how we gonna do it, you know? So let's keep some K value, K1 and K2. So K1 is 1, 10 to the power minus 7. The K2 is equal to 1, 10 to the power minus 5. All right? Simple. So in centimeter per second, this is also centimeter per second. What is the, how we draw the flow net? First, we need to identify the flow lines and the equipotential lines, right? So the flow lines, the first flow lines, right? Right here. Last flow line is here, right? And so our other flow lines should be spread out in between these two flow lines, right? First and one. So let's say we have one, let's say we have two, and then this is the third. Okay. All right. And then we should have the drop. I'm not considering anything, any changes here for, you know. I'm not considering any changes anywhere yet. I just draw my first try, right? Now I have it changes in that layer. So at the beginning, I consider there is no changes.
It is in layer.
In layers is as it is. Okay. So if it is as it is, then what can we do? First of all, according to the rules, we need to adjust these two flow lines first, right? It is going from low perm,
Less permeable to high permeable.
yeah, less permeable to high permeable, right? So your flow line is going toward or going further, closer or further. Light is coming from
Heavy medium to
lighter.
medium.
So it move away.
It will move away from the perpendicular line.
It comes from the air to water, then it comes closer, right? So from water to air, it goes further, like the other way. Okay, so it should move further. So to move further, what we should do, let's say we adjust it. So this line, the angle will change, right? So the angle will change, it will go like this and should be joined, right? Now, if this angle is changing, so if this angle is changing, what will happen here is pretty much looks like this. I just adjusted it. I didn't do anything else in my first. Right, you know, so if you look at this, my flow lines are getting smaller, right? Okay, next part, next you see there are some other difference in between these two lines here, right? So we can accommodate another flow lines. So if you want to accommodate another flow line, what I should do here is I will go backward, not forward. So I will try to draw another line like this. So now I'm going from where? From the
Lighter medium to denser medium.
lighter medium to denser medium. So my angle will move toward, right? So it should go like this, right? Instead, it will go closer, right?
K2 is higher than K1, right?
Yeah,
So it should be
K1 should be denser.
tensor to higher.
no, not denser, it's the resistance. Think about the resistance.
Yeah, the resistance should be higher in K1.
Resistance is higher to chaos, so it will move closer. It will move closer to the particle.
Tensor to lighter, closer.
Yeah, denser to lighter. Just think about how light. So if from the if light is coming from air to water, it will move toward the particle, right? So it's the same way. From water to air, it goes further, right?
Actually, the lower layer is the lighter layer
In terms of resistance.
in terms of resistance.
Yes. That's why it's considered this is air. The bottom layer is air, the top layer is water. So what happens if light is coming from air to water? It will pass toward the bottom layer, right? So your flow net will be adjusted. And this way. So our flow net is supposed to go like this, but it moves closer. Okay. Now, do you need to do any further adjustment in terms of our equipotential lines?
The right one is like, it looks like rectangle.
Which one?
The right.
This one?
The right side.
Yes, yes.
This one, right?
Yeah.
So maybe, but in this one, there is no, you can adjust it, so it's okay. So maybe it will go even further. You know? It will go even further. Could go even further. So the size is adjusted. You know? The length, this length and this length should be the same. L1 and L2 should be the same. So it go even further. Okay, now if you look at the bottom layer, you know, it's already been a rectangle. Now, right? So it's been adjusted.
So we just gonna adjust the flow net, not the equipotension of line.
Either you can do either way. Either you do the flow lines or you do the equipotential. you know. But it has to flow through all the way. Usually you only adjust your flow lines, not equipotential lines, because your flow lines, since it need to travel longer, right? Or you should have higher resistance, there is no way in the flow net we can allow that. In the flow net, if you want to accommodate higher travel path, like higher resistance, the only way you can do it is through adding higher travel path. Right? The first thing that you say. The higher travel path is added to accommodate the resistance difference. Because this is what we can do in the flow. Very good thought. Okay. Any question on this? Still confused?
Shouldn't the equipotential lines also change?
You can change the equipotential lines, but in this case, you need to adjust it. How are you going to adjust it?
By changing the lines.
Yeah, in this for this one, you don't need to.
For this one again.
But you can do it either way. Either you can adjust the flow lines, and if you can adjust the flow lines, that's easier than adjusting the equipotential lines. You know?
So if I'm yeah, the first one, the first point of intersection from the left actually. So if I were to adjust the equipotential line, should I adjust it where it coincides with the membrane layer or where it coincides with the flow line?
Equipotential lines?
Yeah.
I
If I
don't
want
think the
to,
equipotential line follows that the same way, like that. Wait. Equipotential line is equal. It doesn't change the direction. Your flow lines only change the direction.
Here the equation also changed.
Equipotential is not supposed to change.
If I change the flow lines, then the equipotential line should be changed.
Yeah.
According to the
It's here like 50.
perpendicular.
Yeah, you adjust the flow lines, equipotential line automatically get adjusted through this. But for this one, the angle difference, the refraction rules doesn't apply to the equipotential line. The refraction rule only applies to the flow lines.
so when we are trying to adjust the flow lines and draw the equipotential lines, and since we have to make them like perpendicular cross section.
That's it's automatically adjusted with your flow
Got it.
line. Correct?
So that means we need to work on both.
Ultimately, you need to work on both, but you need to keep that in mind. But you try to adjust it only with the flow. Now, if you want to adjust it with the equipotential line, let's say you cannot make it work, then you can add additional flow line, additional equipotential lines for that layer. Flow net can handle only a certain amount of difference. Flow net cannot accommodate. Let's say you have a sand layer and you have a clay layer. Flow net cannot be used. In terms of the flow net, what you have to do is
Subtle change.
you need to ignore the major layers, like the one which will give some resistance, but you just ignore it because through the flow net you cannot do any calculation. Okay. Either you need to use the Geo-Studio, Rock Science, or any other software, or maybe Plexus. Plexus will not give you the flow net. You cannot get a flow net in Plexus. But you can do it in CW. In CW or Rock Science, like Slide, you can get it. Okay. Okay. So what next? What comes next? Any question about?
Oh, ready. asked about it in the morning. Changing in layers.
Absolutely. And what else? Okay, we did it on the piping, two potential lines, flow lines. There are other things, okay, so let's go to the manual. I want to cover more from the manual today. So the first thing is there, two potential lines, flow lines and everything. Now, the seepage manual is, I posted it in campus, it's already there, 1901. So in the 1901, you will find it. So we have two things. One is if we have it two different layers, we just adjusted it, right? For two different layers. But there is another thing that we also need to cover, which is they also have some discussion related to it. This is chapter 3 or chapter 4? Section 8.
Chapter 4 is the problem. Principle.
Which principles, right? Chapter 4. We are close. Confined flow programs. Confined flow programs. Yes, it's coming. Look at this.
Yeah.
You know, so here your number of equipotential line on the top layer and the bottom layers are different. Are different. You know, are different. So your equipotential line, your flow line is adjusted. Equipotential line is adjusted.
It should.
You know, so the same way your equipotential line is adjusted. But the problem I showed, you don't need to. But in terms of your equipotential line, that always goes perpendicular to your flow line. You know, so that's a little bit tricky. So, for example, look at right here. So what happens here? This is a dam, and then this is a sheet pipe. By the way, do you know why the sheet pipe is being added?
To increase the flow path of the flow line.
And what is the benefit?
The creep length increases. The creep length increases. The failure happens further away from the structure. The failure zone, the Tajlagi said that the depth by half is the failure zone.
Yes.
So that increases and keeps our structure safe actually from uplift pressure or something like that.
Okay. Other than that, any other thought? That's a good one. But there is another basic, very basic,
Passive thing.
very basic advantage it offers.
The energy of the flow.
What happens with the energy of the flow? With the sheet pipe?
Breakwaters.
It doesn't let water pass through the structure, below the structure, below the foundation of the structure.
It does.
It does not. It does.
It does. Any if there. Okay, I understand what you're saying, but can you rephrase it in a different way? It doesn't let the water pass through. I understand that. Why?
Because it's impermeable.
Static pressure.
Hydrostatic pressure,
reduction or make it distributed, make it less concentrated.
or more.
Why we have the sheet pipe?
Why we have the sheet pipe? What is the major advantage of adding the sheet pipe?
Prevent seepage, reduce the water head,
How?
which reduces the pressure.
How?
It, so the water should like it's impermeable, so the water will look for easier path, so it will go down. So the difference in the head, it will go horizontally and vertically away, which will change the horizontal. I mean the difference in head, right?
Okay. Okay, the basic idea is, do you have a key? Anyone? Sorry. Anyone had a key?
Key. Yes.
You had a key, right? So let's say your kid is not sleeping. What is the best way of letting him sleep?
Make him tired.
Make him tired. Right? If you make him tired, him or her tired, eventually they'll go to sleep. Right? Means what? You need to drain the energy. Right? If you can drain the energy, they get tired. So how you can drain the energy of the water?
Make it run longer.
Make it run longer. That's it. Ship will do nothing. It just force the water to travel longer. So as the water travels through the soil, it dissipates the energy. The soil do everything. Ship well doesn't do anything. You see. You're just forcing the water to pass through.
Changes the direction of the.
Yeah, you're forcing it. So the best way you can get the best benefit out of it, if you're forcing it in an impermeable layer of the water, of the soil. So then water has to go pass through all the small porous space of the clay. And it's very difficult to pass through it. So it dissipates most of the energy.
Ultimately, water will be stored there. Like
Water will pass through up to the point it can pass through. And then it has no energy left. So it cannot pass through. Right? Okay, good. The same thing, you see, the same thing. If you need to adjust it, you only need to adjust it when there is a lots of difference in between the permeability. You know, when there is a significant difference in the permeability, you need to do that. Very important. Okay, so in this one, they also talk about it, and it's just like you have a difference between the flow lines and the differential line. So this manual explains it really well. You know, this manual explains really well. I suggest you to read this part, especially this part. You know, this part is very, very important. It's like how to develop this. They explain the methodology. I'll cover that, but guideline for the flow net drawing. This one is very important. You know, page 411. So from page 411, read all the way and follow all the steps. You know, this is the best guidelines to draw a flow net. The best guideline. No book, no manuals explain it that way, other than this one. Okay, so that goes with one thing. If you have two different layers.
one single layer.
Now let's say in between the two different layers, you have anisotropy.
Both layers have same K.
So far, we discussed both layer has same K. Now let's say both layer has a KB and K.
Things got real messy. This place sleeping.
It follows the same way, honestly. The same principle applies here. So what happens? You need to do the adjustment between your flow line and the equipotential line, right? So let's say when it travels vertically, it has a certain loss, but when it goes horizontally, it is a different loss, right? So all you have to do is you need to stretch it in the square root of it. Why the square root of it? Any idea?
Square root H kV.
A count is square root kV, right? Isn't it? So you take k square equal to k p and kh. So you need to adjust it in a power range, right? Square. So if you look at the rules, what you have to do is flow net for anisotropic soil. You just need to do the adjustment in terms of the scale. No, it's very simple. It's very simple. It's not a, oh my God. What happens here is, let's say we are trying to draw, there are two ways. I'm trying to give you the easiest way. So the easiest way should be, let's say in this one, we have a kp and kh. Okay, so this is kh and this one is kp, right? So when we draw a flow net, what happens in the flow net?
There is sequence line, there is flow line, there is equipotential line.
But there is a basic thing in the flow net drawing, which is flow net is a graphical method, right? So every graphical method has a unit, like a scale. So you have a scale, certain scale along the horizontal direction and the vertical direction, right? Equal scale, like in a graph paper, if you were plotting something. But have you drawn something in a graph paper with two different scales?
Yes.
You did, right? So why don't you just adjust your scale so that your kp and kh has the same weightage in your graphical scale, right?
In that case, nothing will change.
In that case, nothing will change. You just follow the same way you draw the flow net, right? That's the most easiest way of doing it. This problem is not messy. It only gets messy when you have to do the uplift calculation. You know, so let's say you have a concrete dam like this, and in the concrete dam you have some water. So I'm giving you the problem for the next time. You have the water. Let's say you have a sheet pile here, and then you have two lids, right? And then this two layer has two different K1 and K2.
And kh.
And KH and KB.
Any more variable?
Any more variable is not needed. Right? Okay. So how it should pass flow through the soil? It will come, goes all the way, goes up. First layer, right? Okay, I haven't applied any K1 and K2. So this is your KP and KH. Okay. And your KP is greater than KH. Sorry, KH is twice KP. Usually your KP is KH is higher. right? Anisotropy. So your kV over kh, kh equals twice kV. kh equals twice kV. So what do you have to do? You have to do the adjustment, right? So you need to do a square root of kV by kh, right? So if you take a look here on this one, your kx equal to 6. Sorry, what is x? It's not clear. K1 and K2.
X is horizontal.
X, is
K
double
is horizontal and K is vertical.
Okay, so this is kz. So let's say you have, so your factor for anisotropy is 6, right? So what you have to do, you need to adjust your scale. So right here, your vertical scale is 10, right? Your horizontal scale is
24.5.
10 multiplied by square root. You are adding it up. So you can do it in two ways. One is this way, and the other one is the same scale. You can stretch it. Every point that you drop, you multiply with this factor.
Changing the scale on is easier.
Changing the scale on is easier. No doubt on that, right? But if you're changing the scale, then something else has to be adjusted. You know, something else is what? Right here you have a sheet pan, so you don't need to care. But how about you have a dam on top of it?
Then we need to change the flow lines also.
No, you don't need to. You just need to squeeze the dam.
Dam is to be squeezed.
Dam has to be squeezed. The flow rate should remain the same, but the dam has to be squeezed.
Because we are adjusting horizontal scale.
Yes. Since our horizontal scale is different, so whatever the length of the dam, so let's say in the previous one dam is, let's say 50 meter, which is very big number. So instead of 50 meter, now the dam should be squeezed like this, right? Dam should be squeezed like this. So if you squeeze the dam, it solves the problem. So as if nothing happened. Right? It's not a difficult problem. It's just the trick. You just need to know the trick.
So many tricks and one problem.
So many tricks and one problem. Yes, that's true. So in this case, now your uplift force has to be calculated. You know? Remember that. So if there is anisotropy and then there is the dam, then you have to adjust the structure. You have to redraw the geometry of the dam and then do the calculation. Okay? Do some practice problem. There will be some problem like this in the meter. Okay. And okay, any question up to here? I already covered two methods. I only have two other methods to finish the class. So that will take maybe another 30 minutes.
The one of like graphical method, right? What was the another? You said two methods, but all we're talking about like graphical method.
Yes, I covered two methods. One is your K1 and K2 is different.
Oh, okay.
So,
Fine.
two layers.
Yeah.
And then your KV and KH is different. So what happens if your K1 and K2 and KV and KH? So you have KV1, KH1, KV2, KH. How do you do that?
you know, like 1 kV for each layer.
Yeah, you have K1, KP1, KH1, KP2, KH2.
So we'll like calculate the horizontal equivalent of KH. And again the vertical equivalent of KV. Then we just square root within dot matrix actually. Root K equivalent V into K equivalent H.
H and do a line.
That should like give us the total K, right?
That's give you the total K in terms of the flow calculation.
Mhm.
When you try to calculate the flow, Q equal to K H A N U over NF over NG, right?
Yeah.
So in that K, you has to be calculated based on that. So one problem covers everything that you have done. All the homework problem covers in one problem, right? So you need to calculate the K. That's one. And then how you draw the flow rate.
That is the difficult part.
We'll just adjust the scale,
You need to adjust the scale.
then we draw the program.
And then if you have any structure on top of it,
Then we just squeeze the structure, nothing changes.
Nothing
According to the
changes.
scale.
and then if you have a different K1 and K2, means like two different layers, then how you adjust it?
I would prefer to just scale it.
No, scaling is needed for your K1 and K2. Scaling is needed for your KB and K. But when you have two different layers, you still need to do your
No,
flow rate adjustment.
First, we do the version and then the flow.
Okay, but remember there is another thing. So when you're trying to do, so you're for the transform section, this is the thing, like your horizontal scale is 1/256 of the particle scale. So this is the formula. But another thing is, so for example, look into this problem. So you have a problem here. This is given. So you have two different layers, KV and KH, right? So instead of adjusting anything, always being done here is your dam is squeezed. Yes. This is the original length. And this is the adjusted length, right? So dam is squeezed. Correct? Okay. But your dam is squeezed, you calculate your kx, ky, you got the adjustment, you come up with the Q. That's for one layer. How about two different layers? How about you have two layers? Both of has the KP and KH. Then how is gonna do it?
Like two different layers with two different K.
KP and KH.
Okay. So
Squeeze the dam.
First squeeze the dam.
then we have to adjust the flow line. Adjust the flow line at the intersection of the layer.
Okay, but remember, when you're squeezing the dam and you have two different lines, so means you have two different units.
Can we do two
So-
squeezing? Two times squeezing, first transformation for the first layer, then considering the second layer, we can transform again.
Maybe you can.
Take the smallest one of the scale and then squeeze it with other things.
So then like we have to scale like what do we say? Two origin need to be scaled, like horizontal need to be scaled for the two different H, and the vertical need to be scaled for the two different V. Then we draw the flow line.
Okay, the answer is it's very tricky because we need to adjust with two different scales, and that's almost impossible to do it. So you cannot do it. So the only way you can do it is, let's say you have a KV and KH in the layer 2. So from there, find out the equivalent K. So if you find out the equivalent K, your life will become very easy. So you just do the adjustment for the layer 1, because if you do the uplift calculation, you need to do it anyway. And after you do the adjustment, then you just follow the K1 and K2 rules.
So adjustment the scale first and split
You
it down.
scale it always with the layer one, the top layer,
Mhm.
because your structure is sitting on the top layer.
And for the.
And the second layer, just come up with equivalent K and do the problem.
Can you do this equivalent thing with the first layer?
In that case, you cannot do the uplift calculation. Correct? So for your uplift, if you don't need to do the uplift calculation, you just need to calculate the Q. It's okay, you can do that. But if you need to do the uplift, then you cannot. Because for uplift, you need to adjust your scale anyway. Otherwise, your uplift calculation is wrong. Same goes for the exit gradient. If you need to calculate your exit gradient, you also have to do that. You need to follow the flow net. So for these two things, you cannot. But just for the Q, if I just ask you to calculate the Q, it really doesn't matter. You just come with the flow net, equivalent one, equivalent K, and then do the calculation. It's okay.
The problem is if you ask us about the uplift calculation with two different K having two different. Next one, it doesn't get to that.
Then you have to play with it. Okay. But think about it. This is what is needed, because as long as you can do one problem, you can do all problems. That's one problem is the killer problem. If you can do that problem, you can do any problem on flow, right? Because if you can do that problem, you have to be crystal clear in terms of the flow. You cannot have any confusion. If you have a confusion, you'll get stuck. Okay. All right. So I'll give you a 5 minutes break to come back, and then I will do 2 other problems, and then we're done for today.
There is no voice, Dr. Khan. Dr. Khan.
Yeah, trying to fix it, Omar.
Oh, okay.
So the question is how we can draw the flow net for an embankment. Any idea? Anyone? Any idea? Homework?
Well, I will assume that we would first define the I mean, the seepage line, which is the water path and the embankment, and then we'll have the drops perpendicular to that line going down.
Okay, very good, excellent. And then we just need to follow the regular way of how we have how we draw the flow net, right? All of our equipotential lines that draw perpendicular to our flow lines. And we need to find out like what is the top and the bottom one, and it goes like that. Anyway, very good. So that is the graphical way of developing the flow net, you know. So that method has different numbers. So, but the first thing is we need to learn how to draw the flow net. Okay. So to do that, it has some rules. Basically, for a embankment, we have a flow lines. So our outer periphery meter, our outer geometry is this. This is our geometry of the embankment, you know. And then our flow lines or the flow lines start from the top of the embankment. So this is our water table. You know, it intersects with the geometry at point B. So from point B, usually the flow lines go, it's a very typical line. Looks like this, but very typical lines. You know, if you look at my line, goes like this. Like this. That's the most typical lines. You run any analysis, you will talk with a flow line looks like this. So in this point, there are a few different points, B, C, D, and A. You know, there are 4 different lines, that 4 different points that we need to graphically establish the seepage line. You know, so this is the seepage line. This is the top of the line, within them. Now, how we can do that? It comes here, from here. You know. So our starting point is, let's say we have our geometry. So these are our points within the geometry. Okay. These are the points within the geometry. What we have to do is from this point, we need to find out from this point. First, we need to calculate the M. So what is the M? M is the distance from one point to the top of our water line. The distance, which is M. All right, from one corner point to where the water is touching the back slope, you know, or the river side slope, or the reservoir side slope. That's the distance M. Then we need to calculate 0.3 M. Okay. So once we calculate the 0.3 M, that is our point A. We take point A and we take point D and we draw an arc. All right.
0.3 and
That's 0.3 of A, right?
0.3 of n. Yes, 0.3 of n. So from that point, we draw an arc, we get E, which is y naught.
But let me interrupt you. Where do we get the point A?
0.3 n.
from B.
point B.
0.3 and
The
distance
starting
is
point to the is N, then from B to
0.3 n. Okay. So then it's going to intersect at point E. So the difference between these two is y naught. So now we need to find out the y naught by 2. All right. So from that y naught by 2, our game started. So the first thing is to find out the point F, which is the y naught by 2. All right. So now there are a few points. Those are really important points. Which are the most important points? The first point is point F, and the other point is point A. All right.
So how do we draw the arc from A to E? It's a
Center is D. Center is D.
Center is D. For that one, center is D.
We can find out the point E,
Yeah.
the distance.
Yeah. You know DAD. So you have a radius of AD, and you just draw an arc with this radius AD. All right. Then you have point A and point F. So this is point F, point A. The very first thing that you need to do is draw a line between A and A. Okay. And then draw another line. So first we draw the line A and A. We take a scale or ruler and draw the line N. And then you try to draw another thing, which is you draw another line, which is O and F. So what is O and F? You know,
GNA.
or GN. So GN. So what is the GN? What is the point G? You extend the water line all the way, right? And you extend a vertical line from the point A, right? So you get the GN. So you get this point. Now, what you have to do is, now you have a distance between G and A, and you have a distance between G and F. So let's try to break it down into equal size distance. So let's divide it in between 5 to 6 points, both of the line. Okay. So let's say from F, G, and F, we break it down into 6 points, or in 5 parts. So from these are all equal distance, you know, we just break it down in equal distance. So how many points we are breaking it down? 1, 2, 3, 4, 5, 6. 6 different points. 6. So if we are breaking it down between G and F in 6 points, we'll also break down the A and G in 6 points. Equal distance. So right here we have 6. We also have 6 here. If let's say we break it down in 7 points, on the top it should be 7. If we use 5 points on the top, it should be 5 points, like that. Okay.
Is there any minimum requirement of spacing that we need?
5 to 6 is minimum. You have more points means your car will be better, you know, more final. But for any parabola, you need minimum, no, 3 points. 3 points will never give you a parabola. Three-
5 points.
you need 5 points. If you want to get the accurate curve, 3 points may be okay with the circle, arc of a circle, 3 points. So this shape is a parabolic shape. That's why you need more points. Now, what we do is we name all those points. So we have a point 0 from here, right? So it's 0 here, so 0 to 6. And then point G is our starting point, so it's 0 to 6. This is 6. All right. Now, all we do is, so between G and A, we break it down into 6 points, equal distance. So it's 1, 2, 3, 4, 5, and 6, right? And then we do what? We draw
Draw the 6 line.
We draw a line from point 0. So 1, 2, we draw this line, right? 4, 5, and 6 is already been drawn, right? And then we draw horizontal lines from each of the distance. 2, 3, 4, 5, 6 is already drawn, right? Now, all we have to do is we need to find out equal points. So 0, 0 is this point, right? Or is 1, 1. So 1, 1 is this point, right? Or is 2, 2. 2, 2 intersecting this point. Then to find 3, 3. 3, 3 intersecting this point. 4, 4. 4, 4 intersecting 4, 4. 5, 5 intersecting 5, 5. And then 6, 6, right? Sorry, 6, 6, 6. 6, 6 is here, right? Now we join all the lines, starting from 1 to these points. Okay? We got this point. Now we do what? It's a partial seepage line. It's not the full seepage. It's a partial seepage. So let me erase everything again, and then just redraw the purple line. Okay. Okay. So basically, we have this point, 4, 4, right? 3, 3, 2, 2, 1, 1, 0, 0, right? So let's say we have this point like this, but we need the original point. So our original point, what is our initial point of water intrusion? Our water table is here, right? Our water table is intersecting at point B. So from point B, it should intersect with the seepage line, not from point A. So, and our flow line, the first flow line, which one is our first flow line? Or which one is our first equipotential line, not the flow line? So this surface is our equipotential line, right? This is the draw, the first draw. So our flow line should intersect in right angle, right? Perpendicular. So from here, first we have a perpendicular line. And then that perpendicular line should have a smooth transition to the flow line. So we start with a perpendicular line and you should have a transition to the flow line. Right? Our last drop is what? Right here. Right? This surface is our last superficial drop, right? So our flow lines are going to be adjusted here. Sorry, this is not equipotential line, this is a flow line. Our flow line is ending here. So the flow line should be smoothly adjusted with the outer line. So what happens here is it just starts here and then we adjust it and ending it right here. So this is our sequence, the top sequence, which is our flow line, right?
So the ending will be in the F.
Yeah, ending would be not in the F, if ending starts earlier,
Yeah, it's gonna be on the D.
not in D. Not in D, it ends right here. So your line ends right here. It gets a smooth transition, yeah. Because your water is, see, this portion is already out of the embankment. Right? It's already out of the embankment. It means you already have that area wet. The water is already being coming out from this point. So it will just create a smoother edge with the line. So we got our first flow line. So our first flow line we have, and our last flow line is here, right? We got two different flow lines. So where should be our other flow lines?
In between them.
In between them, right? Up and parallel.
So which one is the ask potential line?
So these are our flow lines. So what should be our equipotential lines? I'm answering your question. Our flow lines should be perpendicular, right? Like this. So our equipotential lines are, this one is also equipotential, right? Correct? So how many equipotential? So how we can calculate our seepage? How we can calculate the seepage? Q equal to
Yeah.
NF divided by ND.
K
Yeah, no, over.
ND. What is K? K is given, it's just one layer, right? So you have a K. H, what is H?
In the
Height of the water.
Mhm.
What is NF? Number of flow line.
1, 2, 3, 4.
1, 2, 3. And NF is 3. What is ND? 1, 2, 3, 4, 5, 6, 7, 8. This one? One, 2, 3, 4, 5, 6, 7, 8. It ends here.
I counted from the first layers.
Okay. So that's 8. You plug that up.
So for this problem, like she said that if she count from the top layer, it's 7, but if we count it in the bottom layer, it's 8.
Yes.
So every flow line shouldn't have the same equipotential line. I mean,
Sure. Yes, it should.
so it should be like 8 all over, right?
Basically, it should be, the last one should not be here. The last one should not be here.
Consider the last one.
1, 2, 3, 4, 5, 6, 7, 8, 9. No. The last one is can be here. You need to calculate at the bottom layer. Of this one, you have to calculate at the bottom layer. Because what happens, your water already got released there.
It's flowing on the surface. of
Yeah,
the-
so it ends there, but on the bottom part, you already have some drop.
They haven't considered that the starting of the dam, they haven't started that one.
Where?
They haven't counted the, for the number of drop. They haven't counted the first one.
They should,
They started from like the second,
they should, they didn't do it right. There is no reason not to count that.
so it will be 11 in that case.
Which one? On this one?
The number of drop,
Here? Yeah. Yeah, this one, they don't do it right, but look at this. Do you know who is WES?
what environment society,
World Evolution Service.
that means that.
No, not that, not that.
Any idea what is WES?
Wetland ecosystem service.
Omar, what is WES?
Waterways Experiment Station, ERDIC now.
Already.
Yes. It was the previous name of it.
They used to call it WES until I think the 50s or 60s, something like this.
He is still there are some signboard. If you go there, you'll see. So this method is prepared by them. It's developed by them. And let me also show you this. Where is the? It's not here. The name is not here. It's supposed to be here. All the manuals of the Army Corps is made by Arabic. Every manual.
Coastal engineering manual, there are.
Not only coastal engineering, coastal, Arabic has like 5 or 6 labs. Each of the labs come up with their own manuals. And it all comes in from Pittsburgh. So don't understood Mississippi.
Yeah, all the EMs actually, they wrote.
All the units, right?
Yeah.
All the units. Unless it's written by Arabic, I think Core cannot use it, right?
No, we use all the EMs.
No. What I'm saying is Core for any kind of design, Core need to adopt. First, it should be part of the EMs, right?
Yeah, we actually like 90% of our designs are part of the EMs. We just follow the EMs.
Sure. Okay. So that's our method 1. And then the second one. What happens if you have a horizontal drain?
We did.
Then this point would be like shorter.
Yeah, all you have to do is just need to shift one, right? So to shift it over there, we had the y naught by 2. Here we have a naught. You know, so goes a little bit further into that horizontal drain. That's it. And all other part is same. You know. So basically, this is y naught equal to 2a naught. So this distance is y naught by 2. The same way.
Same. Just the notations are different.
The notations are, only one notation is different, that's it. Other than that, everything is same. Nothing changing. You know, so all we have to do is we need to start from this point to here, break it down into 5 or 6 points. The top one, break it down into 5 or 6 points. Then you can just have like all those points. So this is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, you know, and 6, 6, right? The only part here in your penetration is your starting point from B, and from the B, it should be right angle, right? And then you have a smooth transition. So from the right angle, you have a smooth transition. And then this part, there is no release. So it's all still within the soil. So you don't need to do any adjustment at the bottom part. So you got your first line, and then you can create your second line, right? And then the drop should be like this.
Why is this starting in the mid of the horizontal train, not in the edge of the train?
Yeah, it travels a little bit because you're all the flow point. It's not only one point. You have the flow. So it travels a little bit further. Got it? Any question? There is no homework on this. I'm not assigning on any homework on this, but do practice.
So here in unit 5,
Count at the 1, 2, 3, 4, 5. Yes, 5.
Drop is 5.
Yeah, drop is 5 and flow is 3.
So, back in the days, they used to do it like this, drawing in a graph paper. But do we have any kind of software for this right now? That you can use like rock formation or?
Yeah, it's there are 3. Basically, two software. They are the leader in this industry. One is the slope W, the other, basically the slope W, CW was the leader. Now slide is also doing great. So basically these two software are ruling this industry in terms of the super scale. So we'll do that. We'll do that in the ending. Your project 2. We'll be doing the same thing on the software. So project 1 is doing everything by hand calculation. So I'll assign the project maybe tomorrow, and then but for this course I made the project like in a group. So you already have to have the group, right? The same group applies for the project. And for this one, the project will be due by October 10, 2 weeks. Okay. But the midterm is next week. So if you want, I can extend it. I can make it 17.
The project will be.
I'll assign the project. The project will be doing everything by hand calculation. I'll give you a problem that you have to do everything. You have to do the secret calculation and coming up with the solution. So in that one, you need to do everything. Means you need to do everything. Means you need to do the uplift calculation, exit gradient. You need to do all the factor safety calculation. Then you have to do the secret calculation, and then you have to make sure the seepage is within the limit. So if the seepage is not within the limit, then you also have to come up with a alternate design, and then you have to do the calculation for that.
Do the calculation again.
That's what the purpose of design.
Thank you.
It's kind of like forcing you to do everything by hand calculation. So once you do all the hand calculation, you learn. So if you learn it, you never forget. Unless you do it by hand, you never learn. And nowadays it becomes so easy. All you have to do is you just need to open up all the videos. So that's it.
So, this will be in the midterm, right?
Yeah, this will be in the midterm.
Midterm will be take home.
Okay, midterm can be taken take home, but for the midterm, I cannot give 1 day. I'll give one night. So let's say I'll give you from 5 p.m. to 12 noon. Not noon, it's like the midnight. I can give you the midnight. The take home I will give you the final for the final I'll give you 1 day. Because for the take home, I will allow you need to run some analysis on the software. So I'll allow some extra time in that.
For the final.
For the final, not.
Dr. Kumar, there's another question. For the last map in homework,
Yes.
there's no dimension mentioned for the dam.
Like the
For the
cross-sectional dimension in the depth,
where of-
That was on the lens method, right?
probably.
Lens method, you don't need the dimension of the dam. It's just the horizontal distance. And you need the depth of the sheet pipe. In the lens method, is you don't need anything else.
However, last class recording was not uploaded.
Yeah, so it will be deleted.
Yeah, that's fine. Alright, so. Back to the last class. I will find the video.
Yeah, it's being uploaded today. Because in that discussion, I have some other discussion. And I don't. Okay, I cannot make that one. Another question.
there will be a term paper for this course.
Yes. There will be a term paper to project, to exam, and 3 or 4 homework. So we already have 1 and 2, so 2 more homeworks.
So the term paper will be any topic about CPID, right? We pick.
I haven't think about the term paper. I'll check. I can give any topic on the page, but
I think,
I would like to give interest in term paper.
You told us last time that.
yeah, you mentioned last
Uh,
I
time,
mentioned
A problem or something like that.
a case study or anything about CPID.
I was thinking about like in the last we talked about all the problems like how the dam fails,
Mhm.
you know. So it can be a very good topic for the term paper. Like what we have our homework 1, right? The case study presentation, the presentation in terms of your all the failures,
Mhm.
you know. So we can have a term paper based on why dam fails, or maybe a term paper on the impact of the climate change on the dam safety. This can be very good paper. Yes.
In rainfall data. In rainfall data.
No, you just write a review. And your justification, your thought process, the impact of climate change on the dam safety. You can pick any country It can be US, it can be Europe, it can be Africa, it can be Asia.
Dr. Brahma, what is the purpose of this horizontal drain here? What is the purpose of this horizontal drain?
Okay, very good question. I was expecting this question. The purpose of the horizontal drain is to control the seepage. And there are a few things I'll try to cover that later, but I can give you some good ideas. No, I'll keep it. I'll discuss it later. Because if I disclose it, it should be part of your project one. I'll discuss it after project. What is the best way of doing a dam design? You think about it. Because we are supposed to do some reading, and the reading should be in the chapter remedial design, which is the end of this manual. Seepage control in imagine, which is chapter 8. Chapter 8. Yeah, it talks about different things, like how you this is the answer that you're asking.
Oh,
So it should be on this chapter. I'll talk about it later, I promise, but not today. After a couple of weeks, maybe. But you have to show the calculations and you have to present it. So on that one, you need to present it, and then we will have the drainage, the filter design, and the compaction. So after midterm, on the next class, I'll discuss the filter design, and then I'll discuss the compaction, the effect of compaction. So the next class, you guys will present it. So the timeline wise, so this is September 26. September 3rd is the midterm. September 10th, October 10th is gonna be your the topic on the compaction and the filter design. October 17th is your project presentation. And October 24th. So what is the last class? Any idea? How many classes I'm going to get in for the slope stability? Because I'll need at least two class for the software demonstration.
October 10th is for free.
There's a fallback?
Yes.
That's October 4th. That's on November.
There is no.
After there's a,
That's on the spring. That's on the spring. There's a spring break. In the fall, that's before your meet. That's before your final.
Final, yeah.
So Thanksgiving is the last week of November.
Yeah, I think it's gonna be at the end of the semester, so. We probably will have 7 classes from now,
From now,
I think. 4 in October and 3 in November,
3 November. So
and
out
one
of
for
the
the
three-
final.
out of the 3 class, we are already missing 2 class. One, because for 2 projects, right?
Yeah.
So for 2 project, 2 classes gone. And 1 class is gone for the midterm. So 3 classes gone. Out of 7. So we will have 4 classes left.
But the midterm, you said you want to make it on Wednesday, right? So we can take the
Yeah,
class.
midterm is Wednesday. Yeah, at the same time of the class. That's the midterm.
Can't we take the class on Tuesday?
I can. You want class on Thursday? Next week.
Midterm is on Wednesday.
Yeah, we can do that.
Yeah, then there was no.
Oh, wait. The regular time. The class is Wednesday, right?
Yeah, we can take class on Tuesday.
I think he might have his late exam on Tuesday, right? For
We do.
Dr. Wayne,
No.
next week.
Next week you should have a midterm.
Yeah, Tuesday, yeah, because of the meeting. That was
Yeah. Dr. Han is planning to take the class next Thursday. So we'll be.
So there's the fourth class. Do you have a calendar? Can I check the calendar? When is our last?
That should be 8th of November. The exam is next week. Final exam is next week.
Last one, 28 on.
The class should be
28 November is the final.
class, not the final.
That's plus.
Last class is the November 28, but we are missing another class because of the Thanksgiving, right? Do we or we not?
Yes.
Well, actually, October will have 5 Wednesday or Tuesdays, so it's gonna be 5.
Next week, Tuesday.
Yeah, but in Jackson State, the Thanksgiving week, entire week is closed. No class.
Yeah.
You have Dr. Wayne's, that take home.
Can we come after that?
Yeah.
We can come after the exam. This week.
Next week, it really doesn't matter. It will be recorded, so he can watch the recording. But how about like,
How many classes do we need?
two class, at least two class for the software demonstration. So one class for the seepage, another class on the slope stability. So two class on the software demonstration. I need two class on the slope stability, so that's 4 class. And then I need another one more class on the compaction and the filter design. And then I also didn't discuss BABA because the slope stability is also very tricky for the dam. For the dam, you need to learn first the regular slope stability, then you have to learn the special condition for the dam. Because for the dam, there are 3 other conditions that you need to consider in terms of the design. I thought I was going faster, but it looks like I'm going slower. Because I already skipped some of the lecture at the beginning. The first week or the second week, the lecture I tried to cover is squeeze it all together in one class. I thought like I already studied.
We have total 8 classes there.
Yeah, October got 5 Tuesdays.
In total 8 classes we have there, like if we consider next week also.
Okay, so do one thing. Let's make it simple. In terms of the project presentation, I skip the presentation. So you just submit. Okay, so I said one class. So in next week, you just keep the midterm. So no class on next week, but we'll have your midterm submission should be on the 17th. I'm gonna make it on 17th. But your submission should be a group
For the project.
for the project 1. But project 2, I'm not gonna cancel the presentation. So in this case, we will have 2, and then later on, if we need one more class, then I can do that. But for the slope stability, I think it's 2 class. I need 2 class for the slope stability. I'm not sure how many of you have the understanding of the slope stability or have the basics of it. So it's better to go for the slope stability because in terms of the research also it's very important because everything will work with the slopes, you know. So the slope, I really wanted to go for the slope stability.
So next week you're not having a class.
Next week, no class. Okay. Because how many courses you are taking? Three. Yes, so it's for the midterm, if I take class, then it's another question. It's better not to take class on the midterm.
Well, if you want to take, it's not a problem, big deal actually.
You want or you don't want? For me, this is the thing.
Yeah.
Let's do it, let's finish it.
Good. Okay, so let's have our class will be on Tuesday.
Same thing.
So our exam will be
On Wednesday. Exam is on.
Take home, so it will be after that on the camera.
Yeah, it has to occur on the campus.
So when we use the graph paper for the homeworks, the scanning doesn't show the graph so much.
Which one?
Taking picture of the graph paper, it doesn't go so much.
Make your own graph paper and maybe illustrator.
Okay, you can do it on iPad. Right, everything. Or you can do it in AutoCAD. Yeah, it's like in other times, like in previous years, many students do the front in AutoCAD. That's much easier.
That's all. You have.
For project one,
Yeah, for project one, you can do it in AutoCAD.
Okay.
Because all you have to do is you take this and you need to make it in terms of like you just create the blocks, and within the blocks you just draw it. You know, you can use the polyline, and in the polyline it has a curve in the polyline, so you just draw all the points and you can make a very smooth, good looking curve in the AutoCAD.
It will be much easier than doing it by hand.
Yes, so so you can do it in AutoCAD. That's absolutely fine. As long as you understand it. My objective is if you understand it or not. You know, what tools you use, it really doesn't matter. And for this, if you don't know how to use the AutoCAD and learn AutoCAD, that is also a plus. Okay, very good. Thank you. Any other question? Thank you.
thank you so much, Dr. Khan.
Thank you.